Okay, we're talking about using the steady state approximation to derive rate laws for multi-step mechanisms. And in this video, I'm going to work through a specific problem. The problem is here. We're asked to devise a rate law for this reaction, N2O5, sort of breaking down and forming NO2 and oxygen gas. Here's the mechanism. And these are the three steps that I identified in the previous video. So we will identify intermediates and a component of interest, write rate equations. We'll use the steady state approximation to solve for the concentration of intermediates, and then plug everything in, simplify, and derive a rate law. So I'm going to work through this. Step one is to identify intermediates and a component of interest. Let's do the intermediates first. That should be easy enough. If I can get the right color, good. So here's my reaction, N2O5 making NO2 and O2. I can go through and look at these, and looking at it, NO3 is an intermediate. I make it here and eat it up here. Going across NO. I don't remember NO. Right? Also an intermediate. Used up here, N2O5, So those are my two intermediates in this reaction. The other thing, or in this mechanism, I should say. The other thing I'm asked to do is identify a component of interest. And what I mean by component of interest is a product or reactant that I'll use to determine the rate law. And the specific choice takes a little bit of chemical intuition. If I start looking at this, I could choose N2O5. Looking at the mechanism, I can see that it's eaten up in step one, and then it's made by the reverse reaction. It shows up again in step three. So it's three different places where this reagent appears. Doable, but maybe there's an easier solution. NO2, same thing, it's in step one. And then again here in step two and step three, this one's even worse. Oxygen, if I look at oxygen, this only appears once in step two. And so this is probably a smart one to choose. If I write my rate law based on the appearance of oxygen, then dO2 dt, it's made in step two. And the rate expression is NO2 times NO3. This is an intermediate. I'm probably going to have to use a steady state approximation here. So I'll write a rate expression for this intermediate. Again, made in step one, so that's Ka N2O5. I lose it if the reverse reaction goes, so that's minus Ka prime. NO2, NO3. And then I also lose it in the second step. So this becomes minus Kb, NO2, NO3. I could write a rate expression for my other intermediate, NO, but it's not clear to me that I'm going to use that at all. So I'm going to hold off on that for right now. Step two is to use the steady state approximation to solve for the concentration of intermediates. Remember that in the steady state approximation, we say di dt equals 0. So I can take my expression for the intermediate NO3, set it equal to 0. I then solve this for NO3. So I'm going to bring my two terms with NO3 over to the right-hand side. Ka prime NO2 plus Kb prime NO2. Somehow I dropped the NO3. There's an NO3 up here. And then solve this for NO3. And if I do that, I will get something that looks like this. N2O5 times Ka prime plus Kb NO2. That's my concentration of intermediates. Step 3 is to plug in the derived intermediate concentration and simplify a final rate law. This was my original rate law. Here's my concentration of intermediate. If I plug this in, dO2 dt equals Kb NO2 times Ka prime plus Kb N2O5 NO2. Cancel, cancel, equals Ka Kb Ka prime plus Kb times N2O5. That's my final result. Right? This is the rate law. So this is interesting, right? All of these steps, 1, 2, 3, 4 different steps, produce a simple first order expression, which depends on N2O5. Again, this is saying that this first step, N2O5, where it falls apart and makes the intermediate, is slow, right? It depends only on the concentration of N2O5. And once it produces these intermediates, all these downstream reactions go, and they're relatively quick, right? Again, this is not necessarily apparent just from looking at the reaction, but when you go through and solve this all the way out, it's fairly straightforward. That's it. Pretty routine process. Students like these problems because what you're supposed to do is pretty straightforward. There are some questions that occasionally come up. What if I had chosen a different species to write the rate law, right? What if I had chosen N2O5 or NO2? And what happens is you will get the same result provided the mechanism is complete. By complete, I mean that it adds up to the net reaction. If the mechanism is not complete, which I mentioned does happen because kinetic schemes can involve open systems, you can get a different result. So this is worrisome, right? And it leads students to ask the question, well, how do I know which species to choose? And I tried to walk through this a little bit at the beginning. The answer is it involves some sort of chemical intuition. We're able to parse through that oxygen was a really smart one to base the rate law on. Sometimes it's apparent from the statement of the problem. The more practice you do at these things, the easier it will get. The other question that students ask is, well, how do I know if I made a mistake? And this is sort of the best answer I can give you, which is that it is hard to know. These rate laws can be complex, and so it's hard to know if you've got a right answer. But I can tell you that if your rate law has intermediates, you made a mistake. Your final rate law should have no intermediates in the expression. It should only depend on concentration of the reagents that are there. Okay, I hope that was helpful, and I will put some more practices up on Canvas and see you next time.